Thank you very much for that rather elaborate introduction, Dr. Aparna.
Thank you.
It's a pleasure and a privilege to be with all of you and make this small presentation. I was particularly impressed with Dr. Shivkumar's. I'm sorry I could not join earlier, but the responses and the discussion that I could participate in, they were extremely impressive. So I'm very happy to be part of this training program. So in this presentation, perhaps it will be exact opposite of what Dr. Shivkumar presented. This is absolutely engineering and technological issues that I would be discussing on. So this has to do with urban floods, and I'll touch upon a bit about the lakes and how the lakes can provide a resilience against the urban floods. So the challenge is that we receive floods every year. The floods, in fact, are the biggest, severest natural disaster, and we face them every year, year after year. The question that we ask is, what can we do to reduce their, on one side, the technological development has taken place so significantly. For everything, we have a technology available, but we are unable to fix this problem. So the question is, can we use technology as well as the current knowledge to at least start mitigating the impacts of the floods? Floods, of course, we cannot stop, but can we reduce the impact is the question. Now, these are some of the pictures, and I don't have to tell which city, which date, etc. Every city, every year, we have similar situations. This is Hyderabad, this is Bangalore, and I would like to especially talk about the Chennai floods that happened in 2015, November, December. This is a very tragic event because 400 of the citizens, like many of us, uh, they lost their lives. But apart from that, there is a huge property loss of the order of 50,000 to 100,000 crores. This happened because of the losses in the industries. In fact, industries like TVS and so on, the automobile industry, they used to store all their spare parts as well as the vehicles on the ground level, and the water rose to almost about 10 meters in that flooding event. And most of these vehicles that were stored on the ground, new vehicles, they could not be used again, and all the spare parts, etc. So there was a huge industrial loss. And in fact, even after so many years, after 4 or 5 years, the city is still recovering from the deluge. Now, there are several causes, as you must have read from newspapers and other articles and so on. There was unprecedented rain day after day. There were overflowing rivers right inside the city. Adyar River flows there. Just when it was absolutely flooded, there were also high releases from upstream reservoirs. In fact, of the order of 29,000 cusecs, that is cubic feet per second, this kind of a reservoir release was made just at the time when the city was fully flooded. Of course, there is poor, inadequate, and clogged drainage system. Exactly when the system is supposed to operate, it's all clogged. Unplanned growth of the city. All of these are absolutely common for most of our cities. Now, let us look at some hydrologic features. When we deal with understanding the floods, we need to look at what is happening in the atmosphere in as much as the high intensity rainfall is increasing in most of the cities, and also how the watersheds respond to such a high intensity rainfall. You look at these two watersheds, one is completely urbanized watershed, another is a pristine watershed here. The same intensity of rainfall occurring in these two watersheds will obviously present absolutely different responses. The response from this watershed, the pristine watershed, will be smooth and slow and perhaps sluggish because there is a lot of time for the water to infiltrate as well as to evaporate. There is an opportunity for the water to infiltrate, and therefore the water that flows out of this watershed will come very smoothly. So this is a graph. This is a flow against the time. At time t is equal to 0, the rainfall has just started. So it slowly picks up and then smoothly it reduces after the rain stops. Whereas in the case of urban areas, whatever falls on the ground quickly converts itself into runoff, because there is no opportunity for it to evaporate, and because of the impervious nature of this surface, it cannot infiltrate into the ground. So whatever falls on the ground almost immediately converts itself into the runoff. And therefore, as you can see from here, this is the urbanized watershed. The time to the peak is much shorter, which means the peak occurs much quicker. The peak itself is much higher because most of the rainfall gets converted into runoff, and the total runoff that is generated in the urban area, that will be much larger. So these pose a major challenge. Now there is also something that is happening to the atmosphere itself. City after city, we see that the rainfall intensities have continuously increased. There are several reasons for this, including climate change, but the more important and more visible and perhaps more well understood reason is the heat island effect. So we are creating an island of, let's say, tall buildings and so on, constructed material here. So we use materials of construction such as concrete, asphalt, and so on. Then there is a general lack of vegetation, which means lack of evapotranspiration that affects the effective cooling. Then we also generate a lot of waste energy because of air conditioners, cooling systems, etc. There is a air pollution. Then also the tall buildings, they also block the surface heat from escaping. And as a result of this, this becomes an island which captures the heat. And that is why the urban areas are called as the urban heat islands. It is shown, and it is well established now, because of this urban heat island effect, the rainfall intensities around the city, that will be very significantly increased the moment you start creating urban heat islands like this. Now in cities like Mumbai and all, which are longitudinal cities, this happens inside the city, and most of our areas, even if they are wide cities like this, now it is shown that all around the city the intensities increase because of the urban heat island effect. I'll come to the climate change slightly later, but this is one of the reasons. Now you look at again these two watersheds. This is a completely urbanized, both are in urban areas, but this may be perhaps a golf course kind of a watershed, and this is a absolutely paved area. Let's say that the same intensity of rainfall happens, and then we are looking at the response at this particular location. This is the end of the watershed. Similarly, this is the end of the watershed. Assume that they are all the same in size. For the rainfall to come to this point from the farthest point, it takes much smaller time here compared to the same rainfall coming to this point as a runoff. This is called as the time of concentration. Now, based on the time of concentration, then we start looking at how to look at the drainage systems in the city. So I'll give you one example which we have done recently along with KSNDMC, and Dr. Veena has been an advisor for this particular project. We look at, essentially we need to understand, as I said, right at the beginning, that we need to look at rainfall intensities. We also need to look at how the drainage system in the city responds, and complete with the human interventions in the drainage system, including encroachment as well as dumping of solid waste and so on. So we look at the historical data and see how the rainfall has been changing over the past. We also look into the near future and see how the rainfall intensities are likely to increase in the near future, and bring down these intensities into our urban areas and see how the urban areas respond. That we do through two-dimensional modeling and so on. As a result of this, we would be able to tell which locations of the drainage system are inadequate, even if they are flowing absolutely free of any obstructions and so on. Now, on the ground itself, we established several sensors. We deploy several sensors for water level measurement. At present, we have deployed about 40 such sensors. And then we collect these sensors will provide us real-time data. So on a server, we continuously get this data. So assume that you are continuously getting the data on what is happening to the rainfall intensities and how the water levels are rising at different locations in the city. We should be able to take immediate preventive actions as well as use this information and the wisdom that we gain from the historical data analysis, etc., to make adjustments in our land use patterns. Now, right now, with the help of KSNDMC, we have also developed an app which is available on Google Play. Now, in this we were using the forecast that was being used from our SAC Ahmedabad, Space Application Center Ahmedabad. Now we are also looking at developing our own forecast for the Bangalore city, and we do several outreach exercises, etc. So that is incidental. Let us see how we address various points around this. Now this is a Bangalore city area. And KSNDMC has about 100 telemetric rain gauges, and this is a luxury for any city. And Bangalore is an example where such a dense data network is available. We use this and start looking at what has happened in the past in the city. For example, this is the flood event. We look at the newspapers and also get the information on which locations got flooded and so on, and then look at what happened during that period across the city. Not only on that day at that time, but we also look at what happened previous 5 days and the next 5 days. This will give us a clue on how the rainfall is behaving, especially if it is during the monsoon. It has a different character, and typically the convective rainfall, etc., happen during April, May, and that has a different character. So we look at different flooding events in the city and get an idea of what kind of responses that we are getting from the entire city. Now, as you know, in any city, if it is raining here in a particular location, let's say in Etri it is raining, but at IISc it may not be raining at all, or the intensities of the rainfall may be much, much different. And therefore, we start talking about what are called as the localized climate zones, LCZs they are called. And this we did along with our Purdue University partners. For example, if all the high-rise compact buildings, they're all located in one particular region, that microclimate will be much different from, let's say we have water bodies or bush scrubs, scattered trees, etc. And all of these are typically seen in any of the cities. It's not that everything is completely paved and so on. We see a bit of gardening, gardens, bit of water bodies and so on. So we create what are called as the localized climate zones and use this information in understanding how the flooding is behaving. At the same time, we also look at the high intensity rainfall, how it has changed. For example, this is start from 1981, you start looking at the high intensity rainfall. It keeps changing from one location to another location, just looking at the annual maximum rainfall. This is a daily maximum. And this gives us an idea that the high intensity rainfall within the city has a great spatial variation. And then we do some methodological improvements and start looking at how the high intensity rainfall is spread over the city. And typically in Bangalore city, we see that the southwest part almost always gets very heavy rain compared to the other parts. Now, these are, again, I tell you, these are high intensity rainfall. For example, we are talking about 10-year return period rainfall. By return period, I know, I hope all of you know this concept that once in about 10 years, this kind of an intensity is likely to be equaled or exceeded. That's the idea there. So we develop these spatial maps of high intensity rainfall. Now you can see the implications of this. Let's say that you want to put a major industry or major commercial complex at any particular location. you would be well advised to see what kind of intensities you are expecting there rather than on an average. And many of these flooding events that happen in major apartment complexes, etc., they will benefit by using such information. And this information is available at a very fine resolution with our team, as well as many of the IITs are capable of doing it. Now, when we are looking at these kind of rainfall intensities, typically we look at only rainfall. But for Bangalore city, we also see how the temperature has been rising over the past. And as you can see from 1940 onwards, we have a continuous increasing trend in the temperature. In fact, this is no surprise at all. You take any city in the country or elsewhere, most of the global cities, you see a continuously increasing trend in the temperatures. Then for the Bangalore city, we also looked at simultaneously what is happening to the rainfall intensities themselves over the past. This is up to 2003 I'm showing, but right now I have done up to 2011 because as you can see, the availability of data is a major problem in India, but we have been able to do up to 2011. Now, these are the durations. Remember here, these durations do not mean that the rainfall happens only for that particular duration that is shown here. These are critical durations. I'll touch upon it slightly later also. So as you can see here, the farther past, which is 1969 to 1986, if these rainfall intensities were of the order of 60 millimeters per hour, this is a intensity, it would have gone up to 90 millimeters per hour in the recent past. In fact, as you start adding more and more data, this is going further. But as I said in the time of concentration discussion, in the urban areas, the times of concentration are extremely small, of the order of 15 minutes and so on. So we need to go even lower than this, which we did. Can I continue?
Please, sir.
Yeah. So we first look at the historical data, as I said, and then we get a clue that the intensities are increasing continuously. But we need to also look at the future, because whatever we are doing now will affect the future. So we look at both the near future as well as the past future, distant future, and ask the question, how are the short duration intensities, high intensities, likely to respond to climate change? As I said, one is a heat island, because of which the rainfall intensities are likely to be increasing, but also there is a climate change effect. But unfortunately, the climate change models they work at a very high, very coarse resolution. And what we are interested in is the societal systems which work at very, very small, high resolution, small scales. So we develop what are called as the downscaling techniques and bring down the climate change projections from larger scales to smaller scales. There are a large number of methodological details here, but you just understand that from the climate models, we bring it down to the city scales. In fact, the skill now exists almost to the block stage, we can bring it down and then start looking at what is happening to the rainfall intensity. Now, this is a study in Australia, and we have done similar studies for Bangalore. What was typically a 10-year event, which means that once in about 10 years, you could have expected that kind of a high intensity rainfall, may start happening once in about 3.3 years, which means that the frequencies of these high intensity rainfall, these are increasing continuously, and this is a uniform trend all across the globe. So we need to revisit the frequencies. Now, again, I come back to Bangalore, and then we project it into the future, just concentrate on this period, not other periods. Other periods are really distant futures, but this period, 2021 to maybe 2040 or something. As you can see here, this is the observed IDF. IDF is that intensity duration for a particular duration, what kind of intensity you expect for a particular return period. That's the idea there. Now, as you can see, we are interested in times of concentration of the order of 15 minutes, 30 minutes, etc. So we are in this region now, this range. In this range, the intensities are known to be continuously increasing. In fact, for certain scenarios, it can come up to almost 100%, 150% increase in the intensities. And that is what we need to start worrying about when we are looking at the urban floods. Now, this is what happens in the rainfall arena. Now we start looking at what is happening on the urban catchments themselves. And this is a very familiar sight to any of the city dwellers. Now these are the drains which are supposed to carry the storm water. As you can see here, this is a drain, this is another drain, and so on. Now, one thing is the solid waste that we dump, because during the non-monsoon, non-flood period, this is such an attractive open space for us to dump the solid waste. So we use this as a dumping ground. Then there are also other problems, that this was supposed to be a natural drain or natural pathway for the flow of water, and the encroachment happens of the waterways, and that constricts the drainage system. Then there are planned obstructions. For example, we put our service lines also in the drain. Typically, you see this is towards the downstream side, which means it has collected floodwaters from most part upstream, and then it is about to deliver into a tank or something. So this is really the end. And we get a width of about 20 meters, 30 meters, etc. in these drains. And exactly at the time when it is supposed to be functioning freely and fully fully efficiently, exactly at that point, these obstructions come into play and then obstruct the flow. Now, these are unfortunately by design, not by default. And therefore, we need to start looking at how to change that system. Now, I'll tell you what we do there. As I said, we develop some sensors. Now, without touching the water bodies, these sensors will sense the water level, or precisely the increase in the water level. And then we are continuously able to monitor what is happening all across the city through these sensors. And this data is continuously transmitted to our servers. And on the server, we run different scenarios and models and so on. So typically, this is what we do. So across the city, we have about 40 sensors. So initially, we installed just for pilot cases in the Hudimau and Madiwala watersheds. We installed a few just to make a test of that. And then now we have installed 40, and with KSNDMC and BBMP, we are going full-fledged and full hog and installing many more sensors. The idea here is that on real-time basis, you should be able to get what is happening at which location, and how the flood waters are increasing, and how the rainfall is also increasing with respect to time. Then we ask the question, these are very critical events that happen in different cities. For example, Surat, 264 millimeters, Delhi 144 millimeters, Chennai 300 millimeters, and this is consecutive 300 millimeters on consecutive days, Kolkata 370 millimeters, and so on. So we ask the question, what happens to Bangalore city if these kind of rainfall intensities are received in Bangalore city? And we also start looking at how the watersheds respond, and these are the lakes and water bodies which this audience will be interested in. We look at how this watershed responds if such and such a rainfall intensity occurs, and we change the runoff coefficient. The runoff coefficient keeps increasing with the built-up area. For example, 0.4 may be very low runoff coefficient, which means that approximately, in a layman's term, about 40% of the rainfall gets converted into runoff. Now 60% is getting converted. That means the development has increased by 20% or something. Then what happens? Then 75%. Like this, we will be able to provide the locations as well as the depth of the expected rainfall. Now, we also ask the question, suppose we have developed so much, 75% of runoff is being seen for a given rainfall, but we reduce it by some means, let's say rainwater harvesting of 30% and so on, then what happens to these locations? At these scales, it is very difficult to appreciate, but you can see at least some change here. But on the correct scales, you will be able to appreciate, because the locations at which the flooding happens, they themselves change. So this we do for various types of rainfall. As I said, Mumbai rainfall of 944 millimeters. If it happens on Bangalore, what happens and so on. So we provide what if scenarios, and we also look at what happens on the blockages of the drains. We use this actual data on the blockages at several locations, and then show, for the benefit of BBMP engineers, we show because of this blockage, the flooding has increased tremendously because the water backs up. The moment it sees it encounters a blockage, the water backs up, and even if the drainage capacity is adequate, it starts flooding in the location. Now we also use the LIDAR, that is light detection and ranging technique of surveying. One important and interesting aspect of this is that you can actually distinguish between two leaves of or two small branches of a tree. It is that kind of a high resolution surveying. So it gives a very high resolution DEM as well as DTM, digital terrain map. And that is what is important for urban flood planning. And we use all of this information. For example, in IISc watershed, we have a lake created, and then all of these drains, we put it, they drain into the lake, and we understand how the water levels are increasing with respect to rainfall and so on. Whatever we have done on this controlled watershed, we have also done in the city itself. And then the LIDAR survey is of interest. If some of you are from engineering background, you will be fascinated to see this. This is a modern technique. In small areas, you can use just a vehicle mounted LIDAR, and it gives a very high resolution information of the order of 0.2 meters and so on, that is 20 centimeters. So in urban areas, these kind of resolutions are important because, as you know, the heterogeneities are extensive in urban areas, and until you capture that, you won't be able to get a right picture of what is happening in the urban areas. So all of that information we convert into maps like this. So there will be an obstruction of flow because of buildings and other obstructions, and how that obstruction plays a role in building the flood levels. So this is what we do through several modeling techniques to show on the graph using GIS and other tools how the watershed is responding. So this is an example. Now we also identify which are the data hotspots where some data is not available and so on. It's also important for you to realize that the heights of the buildings themselves will not be of importance. The plinth area is what is important, because the obstruction, as long as you are within about 5 meters or some such thing, the obstruction is mainly happening because of that particular obstruction due to building up to 5 meters and so on. So when we are looking at the obstructions to the flow, we don't take the entire three-dimensional, we need not in fact take the three-dimensional images, just the plinth area will be adequate. This is what we do. This is just a animation kind of thing for what we have done. So we do the digital surface model, digital terrain model, etc. And then we also look at the stormwater drainage network and lakes in the Bangalore city. Now this is again thanks to our KSNDMC partners. So this is the actual small water bodies, and in fact, as all of you are aware, Bangalore used to be known as a city of lakes. Now this is a Silicon City now, and we have these 100 rain gauge locations. You imagine that you have continuous data coming from all of these 100 rain gauges, and we have the response from all of these drains that is also captured from the sensors. Then you will know exact situation that is happening on the ground as the situation evolves. So we look at certain intensities of rainfall and see how the watershed is responding at the end of 10 minutes, 20 minutes, 30 minutes, and so on. Now this is essentially to impress upon the planners and BBMP engineers on which hotspots they need to focus on and what kind of flood magnitudes that are of importance. So for example, this gives some kind of a picture animation on how this rainfall intensities will cause the flooding in various locations at 40 minutes, 50 minutes, and then so on. So this is a animated picture of the flood levels rising. When we start at the time t is equal to 0, we put some rainfall, and that rainfall continues for some time. It is also important for you to realize that after the rain stops, it takes a significant time for the watershed to withdraw. So withdrawal time is also important. Now, these are some of the details. We also put it in GIS platform to help the planners. Now, what is of importance is that we look at different return periods. For example, 10-year return period, 50-year return period, and so on. One needs to understand that what was happening at 10 years earlier may start happening at about 3 years now. That is a frequency analysis. But we also need to look at how the watershed responds for a 10-year return period and 50-year return period. So as you can see, what was 4 meters flood depth has come to 7 meters flood depth. And I gave you an example of the Chennai floods, where the water level rose up to about 10 to 12 meters. In fact, the full ground floor was completely flooded in that kind of situation. So it is important for us to understand. Now, as I said, we take also the building maps and then show how the water levels will change at various locations. So I'm repeating with different examples, pardon me for that. And we also show, and these are our own models, we show for a rainfall intensity occurring on a particular watershed, how it responds in terms of depth as well as in terms of the aerial extent, and how it withdraws after the rain stops. Now, there are several engineering and technological solutions used worldwide and so on. One of the things that is talked about for a long time is the porous pavement. And now in our project, we are experimenting that and showing through pilot studies. You imagine that the basements of large, let's say shopping complexes or even residential complexes, we use such a material that it just absorbs the water as it falls. Besides, we also have certain geological formations which are almost like blotting paper. That means whatever comes, they just suck the water. And this is what is an example of the porous pavement. Whatever falls is just being sucked by this material, and these are called as a porous material. In fact, in our project now, we are experimenting this and developing our own porous material for use in Indian cities. Of course, this is not a new concept, but the concept that we need to use is that wherever possible, including the walkways, the pathways, the parking lots, the basements, if we can use this kind of a material and especially identify a good recharge zone. Otherwise, we won't be able to store the flood water because there is no space for storing the flood waters on the ground. And therefore, we also look at the geologic formations and locate the ideal locations for using such material, such that the recharge takes place as rapidly as the flood waters themselves are coming. Now, these are obvious, implementable actions. All of this don't require any rocket science here. But what are important and how we have messed up our urban planning is because as I said, the natural drainage pathways, lakes, water bodies, these have been encroached upon, and we need to have large green spaces. For example, from Hyderabad, Hyderabad started it, but now other airports also have emulated. As you drive from the airport to the city in Hyderabad, you see wonderful rain gardens on both sides. Now, these kind of measures will obviously reduce the floodwaters, and of course, the ecologists and others would be involved in designing such things. Now, there are also other measures such as rainwater harvesting, catchment treatment, low impact development, etc. All of these can be practiced in an integrated manner so that we can reduce the flooding situations in the city. Now, one thing is to simply qualitatively mention that these are all good, but where to do, how much to do, etc., we can answer quantitatively and help the BBMP and other planners. So we study all of these. For example, bioretention cell, then there is a green roof, then permeable pavement. These are all very commonly addressed low impact developments. Rain gardens, rain barrel, infiltration trench, then vegetative swales, all of these. Then we look at one by one. We see, for example, we first identify, is there any open space where some of these can be implemented? And then if there is a scope for a particular type of LID, we experiment that and then show how the flooding can be reduced. So this is, for example, we put a very high intensity rainfall of 125 millimeters per hour and show that if you implement a LID, these are the LIDs that we experiment. With LID, you can reduce the flooding to a great extent. Now, of course, these kind of LIDs will also require space. So we need to look at exactly where you can put these. Now you see here, without LID, it was 4 meters. With LID, it has come to 3 meters. But of course, this is a very high intensity of rainfall. This can be further reduced because we have taken only these 3. About 30% could be reduced because of this, but you can also reduce it much further. Then we look at encroachment of lakes on floods. And this is a slightly old data. We are trying to get more recent data. In fact, with our association with ETRI and our collaborator, Dr. Veena Srinivasan, we are able to get more data now here on the Bangalore lakes. We experiment this also and then show what happens if you start depleting the lakes. So in general, we see that the about 2.6 meters goes to about 4.2 meters. If you, in this small area, if you say that all the lakes are encroached upon. So the lake depletion will eventually cause heavy and uncontrollable floods. Now this is courtesy KSNDMC. We have done this from end to end. So we have a high intensity rainfall coming in. In fact, as I said, we also use the forecast from SAC Ahmedabad, and then we put it into our GPRS network. It comes to a server in KSNDMC. Of course, we also get it in IISc, but the processing is happening in KSNDMC. And then we convert all of that. In fact, now we have put a hydrologic model in between so that we use this information, run an urban hydrologic model, and then show which locations are likely to be flooded over the next 1 hour, next 6 hours, and so on. And initially we put it as a WhatsApp group. This message would go to all the planners, including BBMP advisor, BBMP commissioner, etc. initially. Now we have developed a mobile app itself that's called as a Varuna Mitra. And that is thanks mainly to KSNDMC. We have only provided a scientific knowledge behind that. Now, just a small detail for any researchers who are interested in this. As I said, we want to improve upon the forecast. Now, the forecast of the high intensity rainfall will depend on a large number of factors, including the digital terrain maps and what is happening around the city at that location and so on. So we are now we have set up now at 3 kilometer resolution, a numerical weather prediction model. This is called as a WRF model, that is Weather Research and Forecasting Model. To provide forecasts or to improve the forecast that we obtain from other sources such as IMD, etc., to be useful in the city area. Now, the last point I would like to mention is that floods by themselves should not be looked at in isolation. All of these aspects of urban water, they are all interrelated. So perceiving urban water cycle as a single entity is important. We need to look at wastewater recycling, water supply, and in general, how we manage our water resources, including the groundwater and water allocation, how much you put for industry, how much you put for the domestic purpose, and so on. So all of these need to be looked at in totality and in an integrated whole. Now for Chennai floods, the 2015 floods when it happened, the PSA, that's a Principal Scientific Advisor to Government of India, contacted us and my student, Professor Subimal Ghosh, who is in IIT Bombay. He led this project, including 12 different institutes. Essentially, what we are doing here is that we start with the forecast and then generate a large number of scenarios, including the reservoir levels and so on. So actually what is happening on the ground at this particular moment, all of that information is taken into account, and we develop scenarios of flooding. And this huge number of scenarios, we create a library of scenarios. And our aim earlier was to use the artificial intelligence to pick up exactly what particular scenario comes closest to the ground situation. But right now we are doing it manually. And this is implemented. This was the first of its kind. It is implemented by Ministry of Earth Sciences, and their institute in Chennai has also developed a dashboard, and they have actually implemented this model in flood forecasting as well as in planning purposes and so on. Now, this is another information that I would like to give for whoever is interested in. Under the National Supercomputing Mission, in fact, towards the end, Dr. Shiv Kumar mentioned about availability of all this knowledge to planners as well as the general common public. And through this particular project, we are aiming to provide all of this knowledge, including the modeling frameworks and all the paraphernalia and the databases, etc., on a supercomputing platform, which is available for all the researchers as well as the planners. Now, this project has just taken off. In another 2-3 years, we will complete that. So, in general, then, urban flooding, we need to look at what is happening in the atmosphere and also what is happening at the ground level. Now, this requires, it's definitely for mitigating the urban floods, maintaining good drainage system, etc., is very important, and that does not require rocket science. But even after you do all of this, because of lack of space for increasing the infrastructure, we need to start looking at the urban water cycles as an integrated whole, and also answer these specific questions. For example, are the intensities changing really in urban areas? Can we attribute why they are changing? Is it because of climate change? Is it because of urban heat island effect? Or is it because of anthropogenic interventions? So many interventions that we do at various locations and so on. Then high resolution data generation and hydrologic modeling. All of these are important science questions. So with that, I'll stop here. But I would like to just mention, because Dr. Veena had requested on this, you must be aware of several online courses related with many of these hydrologic issues, because hydrology has been a neglected science, and hydrology has become extremely important now because of the changing situations that you are seeing on all aspects related to water. So there are many online courses available, and NPTEL, that is the National Program on Technology Enhanced Learning. This is a flagship program of MHRD, the then MHRD. You must be able to find courses related with several aspects related to the floods as well as the general hydrologic situations. So thank you very much for your attention. I'll be happy to answer any questions.